Hey, hi everyone. So in the previous video, I was trying to illustrate the idea of how does a capacitor work. So you go through the idea that you want to store energy, or you want to store energy in a capacitor. What you do is you use a battery or kind of power supply to bring charges from one plate to another. That's the idea of storing charges. And if you are able to store some charges by pushing it from one plate to another plate, you are storing energy in the capacitor. Okay, so if you want to use the energy, what you do is you just connect the capacitor to some kind of load. So when the charge being forced out from the one plate back to its original plate, the motion of charges passing through the electrical component, it will result in energy being transferred to those components, resulting in those components to be functional. In this case, the light bulb will light up. Okay, that's the basic idea. So I'm going to bring in a little bit of mathematical details to make everything more concrete right now. So the topic for this video here is we're going to discuss the idea of capacitance. Okay, so capacitance here has a symbol of C. Okay, so because it's a value, the value itself must carry some meaning. So the value of capacitance, if I say something has high capacitance, that means that particular capacitor has a great capacity in storing charge. It means what? It is very capable in storing charge, it's very capable in storing energy. But if I say if a capacitor has low capacitance, that means the capacitor has low capability, low ability to store charge or to store energy. Okay, so capacitance is the ability. Oh, sorry, it's supposed to be in blue. The ability of a capacitor to store charge. Or in other words, to store energy, of course. Okay, so to understand how do we quantify, the value of capacitance, let's try to recall just the situation just now. So if this is a capacitor, if you want to charge it, what happens is you're going to connect it to a battery, right? Okay, so the action of connecting it to a battery will result in positive charges moving from one plate to another plate. Okay, so the net result from our discussion in the last video is there'll be accumulation of positive charges in one side, whereas the other side will be accumulation of negative charges. You can see that the upper plate over here has more positive charges, whereas the lower plate here has more negative charges. Okay, because the positive charges move from one plate to another plate in this direction, because the battery is installed like this. If you flip the battery, it can move in another way. But for now, this is the situation. So you move the charges, positive charges from this plate to this plate over here. Okay, so right now you can see that there's more positive charges than negative charges. So this plate is net positive plate. And you can see there's more negative charge than positive charge in this plate. So this plate is net negative charge. So usually we wouldn't draw it to be that complicated. What we usually do is we will just say that this plate is the positive plate. We just represent it as this one is the positive plate, whereas the other plate will be the negative plate. We just draw the net result after the transfer. Okay, the net result is this plate is positive, this plate is negative. And for your information, the amount of charge gain over here, which we call it as positive Q, must be the same as the negative charge that has stored inside here. Because if you think about it, one positive charge lost from this plate is one positive charge gained in this plate. So if there's 1000 loss in the 1000 positive charge loss in the lower plate, that means there's gain of 1000 positive charge in this positive plate over here. So if this one become 1 coulomb, this one will become negative 1 coulomb, because how much gain over here is how much loss over here, how much positive gain over here is how much negative become over here. Okay, so the positive charge and the negative here, they are the same, so we don't need to worry about whether it's a positive plate we want to look at or the negative plate we want to look at. They are both the same value. Okay, so the result, the accumulation of charges over here, as discussed in the previous video, will result in this plate to be having a higher potential. Okay, that accumulation of positive charges over here causes higher potential for this plate, whereas there's a lot of negative charges over here, so the electric potential at this plate will be a lower electric potential. Okay, so if you want to compare the, sorry, there's not enough space actually. So if you want to compare between this V high and V low, if you want to compare between V high and V low, this is bad drawing. Okay, the potential difference, you can obtain the potential difference by taking V high minus V low, right? This is what we discussed in chapter 1. If you want to find potential difference, take V high minus V low. Okay, in chapter 1, last time we call it as delta V is equals to V high minus V low, right? But right now, in chapter 2, what we're going to do is delta V will now be changed to just be called as V. Okay, so V is the new delta V. Why do they throw away the delta? It's because every time when we talk about potential, right, we are actually more emphasizing on potential difference. We don't really care much about electric potential unless you're in chapter 1. From chapter 2 onwards, you never talk about electric potential anymore. You only focus on the difference in electric potential from chapter 2 onwards. So if from chapter 2 onwards, everything is potential difference, there's no more electric potential discussion, then if you keep writing the delta for every single potential difference, it'll be very troublesome, right? So that's why we're not going to write the delta anymore. So V right now will be representing potential difference. V right now will be representing potential difference. So this V right now is called the potential difference. Okay, in this case, it's a potential difference across the two plates. And of course, you know that another name of potential difference is actually called the voltage. Okay, so this is just another fancy name for potential difference. So we say what's the voltage of the capacitor? Actually, we're just saying what's the difference in electric potential between the upper plate and lower plate. Okay, I'm just worried that some of you might think that this V here is the same as the V in chapter 1. In chapter 1, V represents electric potential. But from chapter 2 and onwards, V is not longer electric potential. V is the difference in electric potential or potential difference. And another name for potential difference is voltage. Okay, so right now, this, because we have V high and V low over here, there will be a potential difference or voltage produced or set across the two plates. Therefore, there's a potential difference V over here. Okay, so because there's a potential difference over here, based on what we discussed in chapter 1, where's chapter 1? Okay, because there's a potential difference over here, there's V high, V low, and there's a distance across them. You know that delta V over D will result in an electric field being formed. So right now, there's an electric field being formed inside. Okay, so this is the same story, just that I'm just highlighting to you the idea of potential difference. Right now it's being called as V, it's no longer delta V. Okay, Why do I go through all the story? Is because I want you to notice that it is the accumulation of charges over here. The charge move. The accumulation of positive charge, the accumulation of negative charge result in this V high and result in this V low. And therefore we have potential difference. This happens, causes us to have potential difference. So there must be a relationship between this charge stored and also this potential difference. And this is where capacitance come in. Okay, capacitance, if you look into the definition, the mathematical definition, capacitance is actually the ratio of charge stored to the potential difference across the capacitor plates. Okay, so if you look at it in terms of mathematical equation, the equation will become capacitance is the ratio of charge stored. So charge stored is Q, right? Then potential difference across the capacitor plate, potential difference is V. So that's why ratio it to V. This will be the equation for capacitance. Okay, so this is the equation for capacitance. It's the ratio of Q to V, and it has a unit of, okay, it's a totally new unit that you're going to learn right now. The unit, if you calculate this, the capacitance unit will be called as farad. Okay, farad, we are going to call it as F. Okay, so based on this statement, okay, sorry. We can sort of see that if you have high capacitance, how should you say? Store more charge under the same potential difference. Whereas if it's low capacitance, if a capacitance has low capacitance, if a capacitor has low capacitance, you store less charge. Under no, I'm just wanting to write stuff. The same potential difference. Okay, so for example, I'm just roughly giving you an example. Let's say example 1. Let's say it's 5 farad. So 5 farad means by if you put it under 1 volt potential difference, if there's a potential difference of 1 volt over here, you are able to store 5 coulomb of charge. That's the maths, right? Okay. For example 2, let's say you have a 10 farad capacitor. So if you connect it to 1 volt potential difference, right now you store 10 coulomb of charge. So do you see that even though they have the same potential difference of 1 volt, how do you have same potential difference? You connect it to the same 1 volt battery. For this capacitor 1, you connect it to 1 volt battery. For this capacitor 2, you also connect it to 2 volt battery. Sorry, let me explain again. For this capacitor 1, okay, let me write it as capacitor 1. Let's do write it as example 1. So right now I have two capacitor. So capacitor 1 is 5 farad, capacitor 2 is 10 farad. So what does it mean? If capacitor 1 is 5 farad, if I connect this capacitor that is 5 farad to a 1 volt battery, what will I see is after I finish charge it, after I fully charge it, I'll see there's a charge of 5 coulomb being stored up here, negative 5 coulomb being stored down here. So that's the amount of charge stored for this capacitor 1, which is 5 farad. There's only 5 coulomb of charge stored. But for capacitor 2, it's 10 farad. This capacitor 2 has a capacitance value of 10 farad. So this new capacitor over here, if you plug in this new capacitor, 10 farad capacitor, to a same 1 volt battery over here, 1 volt battery, what happens is the amount of charge stored over here is no longer 5 coulomb. The amount of charge stored right now is 10 coulomb. So do you see that even though you connect them to the same battery, the same potential difference, but if you have high capacitance, if your C is great, if you have high capacitance, you'll be able to store more charge. So storing more charge means store more energy. Okay, whereas if you have a low capacitance, you store only a little charge even though you have the same potential difference. So if you store little charge, that means you store little energy. So this value capacitance here actually show how capable is your capacitor in storing energy or storing charge. If it's very capable, you store a lot of charge under the same potential difference. If it's less capable, it has a low capacitance value, then you store little charge or little energy under the same potential difference. So we can say that capacitor 1 is more capable. You can say it's more capable. That's why it has a greater C. Whereas capacitor 2 is less capable. Sorry. Capacitor 1 is less capable. What am I doing? Capacitor 1 is less capable. So it has a smaller C. Smaller value of C. Okay. Capacitor 2 is 10 farad. 10 farad is definitely more capable. So because it's more capable, it can store more charge. Therefore, it has a greater value of capacitance. Okay, so that's the idea. It's a value that tells you whether the capacitor is powerful or not. If the capacitor is very capable, it has a great value of capacitance. If a capacitor is very weak in storing charge, it has a low capacitance. So it's an indicator of whether the capacitor has great ability to store charge or weak ability to store charge. It can be represented by this value C over here, which can be obtained by taking Q divided by V. Okay, so that's the idea of capacitance. Okay, let me see if I missed anything. Okay, so if we are all clear what is capacitance right now, we can move on to talk about what controls the value of capacitance. Why certain capacitor has high capacitance value? Why certain capacitor has low capacitance value? So we need to understand what affects the value of capacitance. What affects capacitance? Okay, so in other words, the title for this part will be factors affecting resistance. Okay, so in my way of writing things, there's actually only two ways to affect capacitance. So two factors that is affecting resistance. What am I doing? Capacitance. Factors affecting capacitance. Okay, so the first way of affecting the capacitance, the first way is to talk about the dimension of the capacitor. Okay, so let me draw out the capacitor in 3D so that you can understand what do I mean by a dimension of capacitor. So capacitor consists of two parallel conducting plates, right? So if I draw it, I can actually draw it something like this. So this is the upper plate, whereas this is the lower plate. And they are connected to the wire like this. Okay, so I'm drawing it in 3D. Okay, this is how a capacitor should look like. So if you look at a capacitor, when I talk about dimension, dimension means size, right? Dimension of your luggage, dimension. Okay, so when I talk about dimension, it means size. So what are the things that we can talk about when we talk about size? Well, there's actually two things, right, that you can talk about size. First is you can talk about how wide is the capacitor plate. Okay, how wide is this? Okay, so this one will be called the area of the capacitor plate. So the symbol for it will be A. Another thing that we can talk about when we talk about the size of this capacitor is, or the dimension of this capacitor is, you can look at the distance between these two planes. Okay, the distance over here. The distance between capacitor plates. So these are the two things that we can talk about when we talk about the size of or the dimension of capacitor. So these two things will play a role in affecting the value of C. And the equation that relates them together, I'll immediately tell the equation without deriving it, but I'll sort of explain it roughly. So the equation, it's something like this. Okay, A and D over here doesn't require much explanation. But maybe you'll be curious with the value epsilon naught being shown over here. So this is the Greek symbol, epsilon naught. Okay, epsilon naught here is the permittivity of free space. Okay, permittivity of free space here, it has a specific value. Okay, it's a constant that you can find its value in the constant sheet. I think it's 8.825 times 10 to the power of, let me search. Actually, I can't recall the permittivity of free space. Okay, it's 8.85 times 10 to the power of negative 12. Okay, the unit is complicated. Meter negative cube, kg negative 1, s power 4, a square. Okay, you don't need to remember all these things. Okay, you don't need to remember the exact unit, but actually I think there's a shorter version. Let me write the shorter version. Okay, the shorter version is very simple. You just need to shift the D and the A to the other side. Then I believe you can get the shorter version of the unit, which is farad per meter. I think it's just farad per meter. Okay, you can do this by shifting the distance to the right hand side. So this is farad multiplied by meter divided by meter square. So farad per meter. Okay, so this is permittivity of free space. This value here tells you free space. What is free space? Free space is the space that is free of anything. So if I say there's a space and it's free of anything, that means it's a vacuum, right? There's nothing in it. It's a free space, nothing in it. It's not occupied by anything. So if we are not putting anything in between the two plates, then the space in between the two plates, we are going to call it as the free space, okay? Because there's nothing in between the two plates. So the space is called free space. So how good is the free space in permitting electric field to be formed? Is the idea of permittivity of free space. Okay, forming electric field, electric potential, there's a lot to it. But how good is the space in permitting such thing to happen? Is controlled by this value? Epsilon naught. And because free space in anywhere in the universe, free space is the same free space which is nothing, so the value is fixed. Okay, so if you take this permittivity multiply by the area of the capacitor plates, the two plates should have the same area, divide by the distance between the two plates, you get the value of capacitance. So these factors A and D over here will control your capacitance, because if you make your capacitor plate wider, you will increase your A, you cause your capacitance to increase. If you think about it, it's logical. Why is it logical? Wider plate, more charge can be stored. So greater ability to store charge, your capacitance should be a higher value of capacitance. So C and A should be proportional, directly proportional. On the other hand, D over here is the distance between the two plates. What is it saying is, if the distance get larger, if I increase my D, my capacitance will be smaller. I will have a smaller capacitance. Why is it so? You can look at this thing. Okay, remember, increasing the distance, weaker capacitance. Why is it so? It's because if you increase the distance, you will cause the electric field formed inside to be weaker. Okay, the electric field formed inside will be weaker. So if the electric field formed inside will be weaker, what happened is it will store less energy in it. So if you store less energy in it, that means it is less capable of storing energy. Therefore, your capacitance will be a smaller value. Greater distance, smaller value. Okay, it's because of the electric field that it forms will be weaker. If you pull apart the plates, the electric field form is weaker, so it's not able to hold that much energy, so it's less capable of storing energy. So that's why the C will get smaller if you D increase. Okay, so I think this explains the first factor, which is just the dimension of the capacitor. So right now I'm going to move on to talk about the second factor, which might puzzle some people. Okay, the second factor that affects capacitance is the presence of dielectrics. Okay, I'm going to discuss later what is dielectrics in the next video, but right now just let me tell you what happened if you have the thing which we call as dielectrics. Okay, so the capacitor that we have been talking right now looks something like this. Okay, so this is your parallel plate. This is your parallel plate. But what happened is, what can you change with the setup is, actually you can do something called insertion of dielectric. Okay, you insert dielectric in between the two plates. So what happens is, what you are going to insert some kind of things in between the two plates. So if you insert a dielectric in between the two plates, right now the capacitor will look something like this. The distance never change, the distance between the two plates remain the same. You are just, initially it was vacuum, right now you are filling up the space here with some kind of material. It should be wholly filled up. Fill every space in between the two plates. You're going to fill it in with something called the dielectrics. So it's some kind of things. It can be paper, it can be wood, it can be mica, it can be plastics, but you're inserting something in between the plates. It's called dielectric. Okay, so if you insert a dielectric, what happens is you will cause the space in between to not be free space anymore. Just now it was free space, right? But if you insert a dielectric, right now it's no longer free space. So the equation will change. So if the equation will change, we need to make a bit of correction to the equation. If the equation previously without the dielectric, we call it as epsilon naught A over D, right? But once you insert the dielectric inside, the area remains the same, the distance remains the same, but it's no longer free space anymore. So if it's no longer free space anymore, we are going to call it by just the symbol permittivity. There's no knot at the bottom because it's no longer a free space. So I just want you to take notice that the symbol has changed from having a knot to not having a knot right now. Sorry. Okay, and because we want to differentiate the situation where the capacitor has no dielectric and with dielectric, we are going to call a situation where there is no dielectric, we are going to add a knot to the capacitance. So if there's a knot to the C, that means it's the capacitance without dielectric. Whereas if there's no knot at the bottom of the C, there's no knot, means by it's not, it is with dielectric already. There's dielectric in it, so you're going to remove the knot. Knot represents without dielectric. So with dielectric, we are going to remove the knot. So this is how the equation should change due to the presence of dielectrics. Okay, so there are two things. Is it two things? Okay, there are two things that you need to know when you insert a dielectric. So the first important thing you to know when you insert a dielectric is, first, dielectric increases the permittivity. In between the capacitor plates. Okay, so question, increase by how much? The answer is depends on what dielectric is used. Okay, so different dielectric have different relative permittivity. So this is a new term right now. Maybe I should use another color. And the symbol for relative permittivity is called epsilon r. Okay. So what does it mean by different? What does it mean by increase by how much? Depends on what dielectric is used. Different dielectric have different relative permittivity. Means by if we insert, let's say if we insert plastic, okay, a certain kind. If you insert plastic inside, plastic has its own. Plastic is a dielectric, okay. So plastic has its own relative permittivity. Okay, so let's say if the relative permittivity of plastic is 2, then you increase by 2. Means by the permittivity will double. Okay, if let's say today I insert wood, let's say wood has a relative to permittivity of 3. Okay, let's say epsilon r of wood is 3. Then that means by the permittivity will increase by 3 times. That's the idea. So different material, they have different relative permittivity. If you insert plastic, maybe it's 2. If you insert oil, maybe it's 4. If you insert Teflon or Mylar, different kind of material, different value of relative permittivity epsilon r. So if you know the value of epsilon r, let's say epsilon r is 3, that means your permittivity increased by 3 times. If you insert relative permittivity is 5, then it increased by 5 times. That's the idea. Okay, so from this sentence over here, we can sort of make a conclusion that if our initial situation without dielectric, it should be epsilon naught, right? So the new dielectric after you insert the dielectric will be epsilon r. This is before you insert. Before it's insert, the permittivity is this much. After you insert, the permittivity is this much. So how much does it change? Depends on epsilon r, right? That's why the symbol over here, the multiplier that you put in is epsilon r. Okay, if epsilon r is 3, then the new permittivity after you insert dielectric is 3 times the free space permittivity. If your relative permittivity is 2.5, let's say, then that means by your new permittivity after you insert dielectric is 2.5 times the original permittivity when there's no dielectric in between. So this equation tells you how much your permittivity has been increased, and it depends on the material that you put in, depends on the dielectric material, which has different value of permittivity. Okay, so that's the idea that I want to tell you right now. So how are these things being connected to each other? You can know that the new epsilon, which is over here, the new epsilon can be determined from the old epsilon without dielectric by multiplying the epsilon r. Okay, so every single dielectric that we insert has a value of epsilon r. Insert dielectric of value epsilon r. Okay, so this will result in a change of the permittivity. So I just want to tell you right now, immediately I can let you know, epsilon r must always be greater than 1. Any kind of material, any kind of dielectric, the epsilon r must always be greater than 1. Okay, so that means by your new dielectric permittivity and your new permittivity must always be bigger than the original permittivity. Okay, because if you insert any number that is greater than 1, 1.2, 1.5, 2, 4, 5, 100, it will only make the permittivity of the dielectric even larger than the free space permittivity. So this value must always be larger than the free space permittivity. So that's why you know that epsilon is always greater than epsilon naught. Okay, so that's one thing that is important. So because epsilon is larger than epsilon naught, this value here is larger than this value, that means by the final calculation, it's the same area, it's the same distance, right? So if epsilon is larger, that means C will be larger. C will be larger, epsilon naught is small, so C naught will be smaller. So how much do they differ? Well, they actually differ by the same factor, which is epsilon r. Okay, so if you do your calculation, if you think about it, the same relation should hold for capacitance as well. So means by if you have an original capacitance without dielectric, once you insert the dielectric, which has a relative permittivity of epsilon r, it will increase the capacitance by a factor of epsilon r. So if epsilon r is 3, that means by the new capacitance is 3 times greater. If you put an epsilon r, a material epsilon r of 2, that means the capacitance is twice the capacitance from earlier. Okay, these two, they are controlled by the same factor, which is relative permittivity. Okay, so that's why if you have a presence of dielectric, it will cause the capacitance to be changed from an old capacitance to a new capacitance, and the factor in which it is increased is controlled by this relative permittivity. Okay, so one thing that many students might, and before we go to one thing that many students might, okay, the second thing, right, I tell you there's 2 points, right, 2 things that is important, right? So the second thing that is important is dielectric. Besides increases the permittivity, dielectric of course increases the capacitance of the capacitor. Dielectric always increase capacitance. So now your capacitance will become larger if you insert a dielectric in between it. Okay, so these are the 2 factors that affects the value of capacitance. By adjusting the area, you can change the capacitance. By adjusting the distance between the capacitor plate, you can adjust the capacitance. By inserting a material that in between the parallel plates, you will also cause the capacitance to be changed as well. Okay, so a few information that I think is important that I didn't write it down. Let's write it down here. Dielectric must be an insulator. Okay, no matter what kind of material you want to use, it's all acceptable, but the most important requirement for that material to be a dielectric is the material must not conduct electricity. Because why? If you insert something that conducts electricity, what happens is the positive charge that got accumulated will just drop back down to the lower plate. Initially, you use a lot of effort to bring it up to the positive to the upper plate over here, right? But because you provide conductor in between the plates, what happens is the charge will feel, there's a way to go down, so you just go down. It's like you shoot water up, but you don't hold it using a water tank, so the water will just fall back down. So if you put a material that is conducting, the charge will just fall back down, then they will not be charged at all. So the dielectric must be an insulator. Okay, so those are the important things I think need to be written down for now. Okay, before we leave the session right now, let me make clear of the names of all these epsilon that you see here. Okay, there's three symbols that I've introduced. One is epsilon naught, one is epsilon r, one is epsilon. So you have to be very clear with the meaning of all these things. If it's epsilon naught, again, it's permittivity, but because there's a naught, it's referring to the basic setup, which is without anything. It's permittivity of free space. Okay. If you talk about epsilon r, the r must represent something, right? The r actually represent relative. This is relative. So it sort of tells you how much does it increase. Increase by 3 times, or increase by 4 times, or increase by 2.5 times. Relative permittivity. But something important to know is there's actually another name for this epsilon r. Sometimes people will also call it as dielectric constant. So each type of material will have its own dielectric constant. Some material will have a dielectric constant of 2, then you increase the capacitance by 2 times. So some materials might have the dielectric constant of 4, then you increase the capacitance by 4 times. It's a multiplier value. It tells you how much you need to multiply up your capacitance, how much you need to multiply up your permittivity. Okay, so epsilon over here represent when you have already inserted the dielectric, it changes the permittivity to a new permittivity, right? So that permittivity is the permittivity of this space over here, which is filled with dielectric. So therefore, we're going to call this term here, the name will be called permittivity, but right now it's no longer free space, it's filled with dielectric already, right? So it's now the permittivity of dielectric. Okay, so this is permittivity of the dielectric, because right now what's in between is dielectric, that's why it's like this. If it's epsilon naught, there's nothing in between, so you use free space. So what's the relationship to jump from free space to dielectric? You multiply by how much it multiplies, which is relative permittivity or dielectric constant. Okay, so I hope you are able to be clear with these 3 values, because students always get confused with these 3 values. But basically, these are the 2 factors that will affect our C. Okay, you cannot change the value of capacitance by increasing the battery. If you change it to a 10 volt battery, a 100 volt battery, the capacitance is still the same. You cannot do anything outside the capacitor to change the capacitance. To change the capacitance, you can only do something to the capacitor itself. So what do you do to the capacitor? Change the area, reduce or increase the distance, put something in between the capacitor plates. You do something to the capacitor, only the capacitance can change. If you want to do anything to the outside of the capacitance, let's say increase the voltage, you will not change anything about the C. What happens is you can only store more charge. You increase V, Q will increase, but C will remain constant. C is a constant value unless you change something about the capacitor. So this is a concept that you'll be more familiar with it as you do more exercise down the road. But for now, the idea is C never change unless you do something to a capacitor. What can you do to the capacitor? Change the area, distance, or insert something in between. If you just change anything outside, you are only affecting how much charge is being stored only. That's the idea. Okay, so right now, this is where I'm going to stop for this particular video. In the next video, we'll try to think about if we insert a dielectric, we increase the C, right? So if we increase the C, does it cause changes to the Q here, or does it cause changes to the V here? How does Q change due to the increase of C? How does V change due to the increase of C? This is what we are going to discuss in the next video, following up soon. Thank you very much.